Imagine a plane flying at 35,000 feet. Passengers are reading, dozing off. Someone is sipping coffee. Suddenly, the captain's calm voice comes on. Ladies and gentlemen, we've lost an engine. For passengers, this sounds like a nightmare. But for engineers and pilots, it's a situation they prepare for in advance. Modern airplanes are designed so that even with serious failures, they remain controllable and can land safely. Today, let's see why an emergency landing is not necessarily a disaster, but often the result of careful engineering. To understand this, we need to look at the principle behind aircraft design. Unlike many machines, aviation is built on one philosophy: things will eventually fail. Engineers don't hope everything will work perfectly. They assume the worst-case scenario and make sure the plane can handle it. This is where the key concept of redundancy comes in, and that's only the first layer in the safety system we're about to explore. Now let's break down the main ideas that make flying safe even under critical conditions. System redundancy. Nothing on board depends on a single component. There are always at least two engines, often four. Hydraulic and electrical lines are duplicated. If one circuit fails, another takes over. To compare, if your car battery dies, your trip is over. A plane has multiple power sources, so the flight continues. Take hydraulics, for example. They control landing gear, flaps, rudder, basically how the aircraft moves. On most jets, there are three completely independent hydraulic systems, each with its own pumps and pipelines. Even if one system is damaged, two others continue working. The same with electricity. Every engine has its own generator, plus there's an auxiliary power unit, APU, and even a small emergency turbine called RAT that can drop into the airstream and generate enough power to keep the essentials running. Gliding capability. Even with all engines shut down, an aircraft doesn't just drop like a stone. From cruising altitude, a Boeing 747 can glide for more than 150 kilometers without thrust. Pilots know the exact altitude to distance ratios and can use them to select a landing site. For example, an Airbus A320 has a glide ratio of about 17:1. That means for every kilometer of altitude, it can travel 17 kilometers forward. From 10 kilometers high, it could glide roughly 170 kilometers, enough to reach many airports. Even over the ocean, pilots calculate ETOPS points, locations where they are always within range of an alternate airport. ETOPS certification. This becomes especially important on long routes over the ocean. ETOPS, which stands for Extended Range Twin-Engine Operational Performance Standards, proves that an aircraft can fly for hours safely on one working engine until reaching the nearest airport. These principles form the foundation, but their value is best seen not in theory, but in real-life events. Let's look at incidents that show how engineering performs in practice. The Miracle on the Hudson, 2009. An Airbus A320 departing New York hit a flock of birds. Both engines failed completely. Captain Sullenberger had only seconds to decide. Using the aircraft's ability to glide, he landed on the Hudson River. The plane stayed intact, and all 155 people survived. This was not luck, but preparation and design working together. British Airways Flight 5390, 1990. A cockpit window blew out mid-flight, partially pulling the captain outside. It sounds extreme, but the co-pilot landed safely because the systems had backups and continued to operate. Qantas Flight 32, 2010. On the giant Airbus A380, an engine exploded. Shrapnel damaged fuel tanks, hydraulics, and electrics. Despite dozens of failures, the aircraft landed safely. Why? Because it was designed to withstand not just single failures, but chains of them. The Qantas 32 investigation later revealed more than 50 separate failures triggered by the explosion. Some displays even gave contradictory information. Yet the aircraft kept flying because engineers had anticipated cascading failures, not just isolated ones. If this had been an older model, the outcome might have been tragic. The A380 survived because it was designed with extraordinary safety margins. The Gimli glider, 1983, an Air Canada Boeing 767 ran out of fuel mid-flight due to a calculation error. Both engines stopped. The crew glided the aircraft to an abandoned airbase in Gimli, Manitoba, landing on a runway that was being used for a drag race event. No one was killed. Each of these cases shows an emergency landing isn't a miracle. It's the result of engineering foresight. So why do planes and crews manage even rare and extreme situations? Continuous training. Pilots spend countless hours in simulators practicing exactly these scenarios: engine failures, fires, total electrical shutdowns. When it happens in real life, they already know the steps. Diagnostic systems. Modern aircraft immediately indicate what has failed and suggest the procedure to follow. This reduces risk and saves precious seconds. Structural margins. Airplanes are tested with huge safety margins. Wings are bent in stress tests until near breaking. Hydraulics are run under overloads, all to prove the real aircraft can handle far more than it will ever face. What's more, every commercial aircraft must pass certification tests before carrying passengers. This includes simulated bird strikes, lightning hits, and complete engine shutdowns. Engineers deliberately push systems to failure in controlled tests, so that in the real world, the limits are never reached. In the 1960s and 70s, flying was less reliable. Aircraft had fewer backup systems, crews had less simulator training, and accidents were more common. But as technology advanced, regulators demanded tougher standards. Today, the chance of a fatal accident is about 1 in several million flights, making air travel one of the safest forms of transportation. So when you hear the phrase emergency landing, don't instantly picture disaster. Modern airplanes are built to fail gracefully, to glide, to switch to backups, to land without thrust. The survival of hundreds of people in such incidents is not a matter of luck. It's the outcome of engineering planned long before the flight. If you found this breakdown useful, don't forget to like the video and subscribe for more engineering stories. And tell us in the comments, what part of flying do you still find the most mysterious? Engines, turbulence, or landings? We'll pick one to cover in a future video.